Okay. I was working in the same file that I presented the before session, but and only made some change. I added this first slide in the idea of understanding morphemes like the power of sets. Then I think that this can help to clarify the uh, the concept of duality that we are using in the next slides.
One comment, you used the word application, and it would be more common to refer to this as a morphism or a mapping.
Yes, I just said that here applications because in his notes, Professor Osiewicz was introducing careful in this subject and used the first applications. I understand that this is a I don't know how to say, but not a precise definition.
Mm-hmm. The reason why it stands out for me is because I would like to use the word application for a different, higher order kind of mapping, right? A mapping that associates something like a value and a function, and then applies the function to the value. So the word application refers to that process, whereas this definition here, at least so far, is just is more fundamental, I guess. These sort of relationships exist even if there is no application, like, for example, in a lattice, for example.
Okay. Okay. Maybe I can change this word. I use it in the title homomorphisms because
Yes.
is the idea generally here. But maybe it is better to use the same word in this part. Okay.
Okay.
But I insist the idea of here of Professor Osiewicz, because he was preparing some notes for teaching.
Mm-hmm.
And then in at that moment, the word morphemes was not known by the students. Then it's more common the word applications between sets, for example. But I understand that maybe in some advanced subjects, this word can have another meaning.
Maybe the connotation is okay, say, from depending on what language you speak, right? Because for me, a sort of a common name for the concept would be mapping, like a mapping between sets.
Yes.
And then you clarify that usually by referring to functional mapping or something of that sort. But
okay.
The main idea from category theory is that this is an arrow, right? That there's a direction, right? It's very important that that A and B be distinguished by this arrow, right, as being different. Right?
Yeah.
Domain and codomain is good terminology, I think.
Yes, in this part this is good because this give to us the idea what is the relation with the other with the direction of the arrow. No? Then I think that these words is. I thought about you use here the categorical concepts of this relation, but because but if we use here the categorical concepts of object and morphemes, then we have problems putting this the power of B to A, no? Because here we are speaking about elements in the object, in the objects, and then there are problems with the use of the concepts of category theory. Then, okay, this is the principal idea, but then I'm going to change this word.
I think it's enough to use the terminology of sets, since it's quite intuitive, but with the understanding that you will generalize this, right? So that we might have not just sets, but we may have spaces and linear mapping between spaces, or we might have points in a lattice and the relationship between, the greater less than sort of relationships between objects. But fundamentally, the terminology comes from set theory, and I think.
Yes, here that's the idea to use set theory and then start with that terminology. But maybe in the future we can use only the category theory concepts, and then speak about objects here and not sets. But I insisted that I don't find at the moment how to write here the power of that relation between objects in this case.
Mm-hmm.
Then okay, but this is the first idea that I wanted to clarify here, and I'm go to the next. Okay, this is the past slide that we commented, and I wanted to clarify here this slide in the different interpretation about the fee evaluation, no? About evaluation. I think this I added here the concept of phi on F, like thinking in this like an operator, an operator that acts on X. I am speaking about the second row in the in this slide, in the formulas in this slides. And in the second row, then we can think about evaluation like one operator acting on X. And if we think in this relation like a functional, like in the third row, then we can speak about one operator like the action of phi on X that is converting in an operator and to X, and this operator is acting on F. I wanted to add these two rows because I think that here we can connect with the ideas of Professor Garrett about the use of matrix algebra for the expression of the algebra. Of course, we are speaking here about operators, but then we can think about the matrix representation of an operator here, and then maybe it is more easy to connect with that's with the way that Professor Garrett is presenting his ideas. Okay.
Yes, so you make a distinction between the operator, say delta x and x. X is right. So
yes,
delta x is the operator.
Delta x is the operator. Yes, delta
but
x
it's the operator, specifically the operator for x, right?
is yes. This is the operator for x. Yes, and this is delta x. That I think that or maybe I can mark this here a moment.
So are these last two statements equivalent? Operating phi on F and phi first on X, the last two lines of the slide?
Yes, Professor Garrett, we can think about that. A moment, I am trying to use the pen for writing here. Not yet. Okay, now. Yes, here these three rows can be considered like a different interpretation of the application file. Then in particular, the second row is an operation. I am going to write again this. That is the definition of the action of phi on F that is going to us one operator. Then in this row, the operator acts on X, and then this gives to us the value of the relation phi F comma X. Then the next, in the next row, here, the operator is phi X, and this is defined like phi acting on F via X. Then if we want, we can understand this like the functional delta X, and that is acting on F. Then the idea is that this operator can be interpreted whatever we consider. For example, this with a representation in matrix form. Then when we use here elements of here I put that elements of the scalar forms, then we can represent here this operator in matrix form. Then we need to find one. Here we are going to have a problem of eigenvalue and eigenvectors. Forget the presentation of this operator, but then I think we can get that solving the problem of the minimal polynomial connected to this.
Before we do that, I could like to ask maybe the connection between the idea that F is an element of F, right, of the scalar field, but previously you wrote F is an element of the Hom set of two objects, right?
Yes, yes, yes.
So it seems clear that to me that I can write X as an element of the scalar field, but not so clear to me that F should also be an element of the scalar field.
Here we are speaking about evaluation. Phi is the evaluation F of X.
So evaluation always maps to the reals, I think.
Yes,
Yes.
yes, the evaluation are maps to the reals, yes. Mhm. And this is defined as like 5 fx. And then, because in more general, but I think that we can use this later, but we can use this kind of relation for going from degree to degree in the algebra. No?
Okay, yeah, that's interesting.
But still, the expression that you wrote in the box, the red
Yes.
box, you write x and f are both elements of the scalar field.
Yes. Mm-hmm.
And I am not sure that I understand that f can be an element of the scalar field.
Like the
At
real
the same
numbers or complex numbers.
But it means like we apply one number to another number, and that is strange to me. Right? I can apply a function to a value, but the function is of a different kind, a different.
Well, if we're just talking about multiplication, it's okay.
But I am not saying that x and f are elements of reals or complex numbers. I am saying here that x and f are elements of scalar field of functions.
Oh, okay.
Yeah.
So you would call both x and f both are functions.
Both are functions. Yes. Both are functions. And the evaluation is a mapping between two functions to the reals or complex to the field.
Okay, and that's phi, a different symbol then.
Yes, to the next field, yes.
But if we use notation, just change the notation a little bit, if we wrote g instead of x, right? So we have two functions, f and g, and then we would normally be referring to this as composition or something, like we would.
Yes, but again, this is taken in this way from the Professor Oskiewicz notes, because he fighted too much for understand this, not like not with x elements of real, for example, no, but x elements of f. Then this is an important idea. And in this way, I use it here x and not a g, for example, because it's some kind of some kind of principal ideas of Professor Oskiewicz fighting against the standard interpretation of function. Then here, what are elements of the R ring, F and X, and then we are working with that idea. In this way, this product that we have, Fx, is a composition product. This is equivalent to a composition of two elements that are both morphisms in the set category. Then that was the idea of using here X.
I don't know if I would, maybe it's a distraction perhaps if I mention this, but it's common in category theory to talk about topos, for example, which is the sort of algebraic equivalent of a set, right? And in that case, in the notion of a topos, we can refer to X as a mapping, but from some distinguished object that we call the terminal object, right? So then we write everything as mappings or compositions of morphisms, so that an element of what used to be called an element of a set is a mapping from the terminal object to some other object, and then a function f is a mapping between two arbitrary objects. So we can then write, the composition of f with x, because both are mappings,
Yes.
So this is using a topos as the underlying sort of categorical structure, instead of referring to set theory, which is like more commonly taught, but not so general, right? Not so. Maybe one might consider that the notion of a topos in category theory is more fundamental than the notion of sets, which came earlier. Where
yes, I think that here I am racing for the way of get more space. Sorry. Here, here the idea is that we have here like objects, sets for example, no? A, B are set.
or sometimes you might call them classes, for example, or something.
Okay, then
Or spaces.
the class of sets, for example, no?
Mm-hmm.
The class of sets. But here we have morphisms, and these morphisms can be F or can be X, for example. Those are morphisms between these two objects that we have here. And in this way, X is a morphism, not an element of the domain.
I like perhaps if you add another object.
Okay.
Maybe you would write just say
See?
I don't know, not 0 but 1, right? It means any set containing a single element. Right?
Okay.
So the class of singleton sets, I guess.
Okay. Okay.
Usually in category theory, we write that as like 1,
Okay.
but we call it an object. And then X would then be a mapping from 1 into A.
1 into
A, into, from the object 1 into the object A. Right?
Okay, okay.
So
Then okay, here we have 1.
yes.
Yeah.
And then an arrow from 1 into A.
Yes.
And we label that X. And so then the application of F to X is the composition of those two arrows from 1 to B.
Okay. Then I'm going to erase here in the way that we can have this.
Yes.
As X value.
I would write F compose X.
Yes.
Or-
X this is F of is like that we call F of X. Okay.
So now if both of these arrows, F and X, and the composition of them are represented by elements of a field, scalar field.
But I think that here we have more problems because if we are speaking about the set category, I think that at the end we are speaking about one monad. Because we have only one kind of object that are sets, and then we have morphisms here that are F, G, and in particular we have identity, for example. And maybe we have X and this is the principal idea. X is one element, not necessarily identity. Not necessary, no? And we, in this way, we can speak about, for example, in the if we use the second row, then we can speak about F of X or F of G or whatever. Because we can build here the compositions in any way, in any way. For example, X of F.
Yes. So this is, to write X of F is strange, right? Is unusual.
Because there are standard interpretation of X that is there is in the conventional literature that think in X like a element of the domain. But
Yes,
but
it's
not
what I asked you to write there, because if we have this terminal object, it's a distinguished object, then we can say that elements of A are always mappings from terminal object to A, and
but
but this means that we cannot compose X with F, right? Because the domain of X as an element is the domain 1. It is not the domain, B. In order to compose F with something, it would have to have a domain of B.
But the problem is that the set, the category of sets are here a singleton. Then is a terminal object and initial object.
Yes.
Yes. Then, but when we speak about morphisms, we are not speaking about the elements of the objects.
Mm-hmm.
In fact, if I am speaking about identity, I can understand this like a representation, a way of referring to the object that we have here, the object A, for example. Then, but it is important here that those are elements of the morphisms in the category of sets.
But when we write F comma X in parentheses, like that first line.
Yes.
Do you mean that like a product, like a Cartesian product?
A Cartesian product, yes. Yes.
Okay, so if you answer yes, then I can say, I can tell you what is this terminal object, right? So, because we can write, say, X comma Y comma Z. We can write, X comma Y, or we can write just X, or we can write the empty product, right? So we can have the same product operation, but apply it to nothing, right? To no things, in which case this empty product becomes the terminal.
Okay.
It's the initial, right? So if you admit that the category has products, then you almost always have a terminal object.
But if we take two morphisms, for example, let FG morphisms in the category, okay, I have to use here I, no? FG in A. They are morphisms. Then I can define an application phi that is an operation, a product, a categorical product. Yes? Because okay, I need more. Maybe I can go to Blackboard is okay?
Yes, sure.
Okay.
I'm afraid that my questions are making us discuss more category theory and not so much
Yeah,
duality.
maybe we should go on further to see what he wants to do.
Yes, I don't want to distract you from what you intend to present, Jesus. But
Yeah, I'm not all that familiar with the category theory anyway, so I'm kind of, it's over my head, category terms.
In fact, I like to present these ideas in categorical theory language, but it is not easy to organize all of this in that way. But okay, if you want, we can continue, go to the next slide. But in fact, I think that we are speaking about different terminology or problems, and then we need to fix them, but maybe in another opportunity. Okay. Then I go ahead. Okay, here again the definition of exterior algebra of multivectors, and again here I wanted to ask your attention here in this definition that we are here putting are the same for Clifford algebra. Then we can say that Clifford algebra is one exterior algebra of multivectors. Is that okay? Not Professor Garrett?
Yeah, that's perfect. No problems. Just
no. Yeah. Then okay, we are in this way, and here we have two kinds of products, but those are products between multivectors, no? Between multivectors. And here it is important in the definition of this kind of product, because this requires this subspace of antisymmetric elements that are are used for generating this subspace.
Yeah, that's like tensor algebra. Yeah.
Yes. And the same is for the twofold, excuse me, here is the antisymmetric part, the antisymmetric product that in this case are wielded with the tensor product, but without the symmetric part. Then we are splitting the tensor products here in one symmetric and antisymmetric part. But all of these are multivectors. Then we have not here forms.
But then this symmetric product of two multivectors is still a multivector?
Is still a multivector, yes. Yes, is an element of the multivector forms. Mm-hmm.
Yeah, it's like reducing the degree.
Yes. Yes. This is the idea here. Mm-hmm. Then we have enough elements for going up and down in the degree of the multivectors with these two products that are part of the algebra. Okay. Then in the next, now we have a multiforms, and those are defined in the dual. And here is there is a problem. One form is
So we introduced this notion of dual is it implicit in what we meant by the vector?
No, because here we are speaking about multiforms. Then here we are speaking about covectors, not vectors. And
okay. So perhaps you like to write space of multiforms on V star.
Out, yes, here is there's on V star, yes.
Yeah, and also the next line.
Yes. Mm-hmm.
But at this point, you don't make a connection between V and then V star.
Yes, in fact, here is the first connection between them, because the scalar form is defined over a multivector. And give to us to the left. In fact, here there is simplicity. How is this?
Do you mean again V star here or V?
Here in this is V.
Yes.
Is V, because the scalar form acts on V. Forget F. Then we here there are implicit the bilinear forms, bilinear forms that are the results of here omega acting on a multivector. Then maybe in the next slide is more explicit this. I'm going to this. Here it is. Alpha and beta are elements of the dual, and then they act over U and B in this way.
Yes.
Yes, I think that here are the relation with the B space, but we are defining those in the dual space.
You're defining the Guzman algebra on the dual space.
In the dual space, yes, in the dual space. Here is we started defining those in the dual space. And the definition of duality are implicit here, but maybe it's more explicit later. Then I think that these two slides are important because we are speaking here about different kinds of objects that are we cannot speak about elements of the of multiforms like elements of multivectors. Those are different. And in fact, those can be wielded from that.
Yeah, it looks like to me that you're just defining your Guzman structure on the covector space, or the V star. No, V star is the valuation, though. It means valuation.
No, excuse me. Here I am using B.
Oh, okay. So
other.
it's just the dual space, then, yes.
Excuse me. Yeah. It's only B is vector space.
Okay, the dual space.
Dual space.
Covectors, then, I guess.
Covectors, yes, yes. Here we are speaking about.
So defining a Guzman algebra on the covector space, exactly the same definition, except we're using covectors rather than vectors.
Yes, but here we have not a symmetrical part.
But we could define, could we not do that? It's possible, isn't it? Or maybe, yeah.
Not here, because we cannot define symmetric part of the product. In terms of scalar forms.
Yeah, that's true. That's true. Yeah.
Yeah. Then, okay, here it is an element that I wanted to put here. And now, okay, this is why we speak about two different Guzman algebra. One is for wielding the scalar forms, and the other one is for wielding the vector forms. And
yeah, you'd have to define a new symmetric product. I suppose you could do that, but it wouldn't be no longer the Guzman product then.
But I don't understand your comment, Professor Garrett.
Well, just as for defining the Clifford algebra, we use the Guzman space. Well, the tensor we use the tensor analysis, the tensor space to define both the symmetric and the anti-symmetric part to get the Clifford algebra. So I suppose we could use a tensor algebra in terms of the covectors, define a tensor algebra of covectors then, and do the same construction.
But there is a problem, because if we, I go back here, but in this definition, in the, I go first to the definition. Here we have a symmetric and anti-symmetric product but this is the exterior product of vectors that give to us multivectors. And in the next, we are building products, excuse me, of scalar forms. And in products of scalar forms, we cannot, we have not symmetric part. Because if we go to the an example of scalar of two Guzman excuse me, of the product of Guzman product of two forms, for example, then if I interchange the product, then necessary we need this, no? Necessary. And this is the problem with the scalar forms, that we need necessary. We have only the antisymmetric product.
Yeah, yeah, but there is a Hodge dual that's defined on differential forms. The Hodge dual. To map that into the covector space, you know, just define what is a dual of a differential form. Becomes an n-1 form, does it not?
Yes, okay. The dual of the differential form are vector forms. Huh?
That's right. So can't we use the same structure for the covector? Well, yeah, okay, it gets confusing.
Okay. Yeah. I am trying to put explicit the problem that I am finding in the way of define the duality concept inside the Clifford algebra using only multivectors, because I think that for the use of duality, it is necessary to consider the scalar forms that are the dual space of multivectors, and then with that we can build the duality ideas. Okay, then then we have defined here two different algebras that are related, but are not equivalent. Yes. Okay. We in this. Okay. This we speak about the last session. Then maybe. But here is the explicit relation between vectors and covectors, that those are used in composition for getting evaluation of these forms. Okay, okay, yeah, and here there is again the definition of evaluation, but now for vector and covectors. No? And here it is in how we need to use both elements necessary for that. Then we can use them for the evaluation, and then we are going to use this evaluation for upgrading and downgrading in the multivector forms or scalar forms.
Maybe before you move this, maybe this is a good point to ask a question in relation to the duality that Dr. Sobczak talked about last time. So in Dr. Sobczak's paper, he wrote that there are two compatible Grassmann algebras. If we take these two compatible Grassmann algebras, one of them to be the multi-vector space, and the other to be the dual, like the differential forms. So again, we have two different Grassmann algebras, but the word compatible was used in the context of actually saying that something like when we write the product of an element of one of these Grassmann algebras plus the product of the other Grassmann algebra, like product, then the result is one, right? Or something like a scalar. Right?
Yes, yeah, in the same algebra, what defines the Clifford algebra. You're putting them together in that way. That the two Grassmann algebras go into one Clifford algebra.
Yeah, so I'm saying, suppose that these two Grassmann algebras are exactly these two Grassmann algebras that Jesus just mentioned.
Yeah, okay, yeah, that's right. Is it possible to create the same structure in this way?
And what you meant by compatible, like when you write, let's see, how did you write this?
Yeah, I took the fundamental idea was the idea of a nilpotent or a null vector. You square a null vector, you get 0, and I took the set of all such quantities. Algebra. I defined a new set generated by all null vectors or nilpotents, and then I use that to define two compatible Grassmann algebras in that algebra of nilpotents. Well, the algebra generated by taking products of these nilpotents. Well, you can see I was trying to get the structure of the matrix algebra. Well, actually, I consider a matrix to be the coordinate of a geometric number, a Clifford algebra. So it's a little different. It's a different. We're dealing with two different ways of the idea of a covector is a separate algebra. It's not really identified in the same spaces. I think that's the whole problem. It's just a different way of looking at things that has been.
But you started with say two different Grassmann algebras. So
in the same algebra of nilpotents.
Well, they're both Grassmann algebras, so they're both nilpotent in that sense, right?
Exactly, and then I define the compatibility condition.
But this suppose that the first Grassmann algebra was the multi-vector, and the second Grassmann algebra was a
covectors.
multiforms, right? Multi-differential forms. So then here, say alpha is like the element of the multivector, and x is an element of the differential form.
Yeah,
These
I'm
are
not
the
making
two.
that distinction. That's the whole
No, but
difference.
you don't make the distinction as such, right? You just say there are two, and they are compatible, right? So saying that they are compatible is something similar to what Jesus is writing here. I think that what you mean by compatible is that
The
it's
symmetric
possible.
product of the two gives one. Well, for the simplest case, we looked at the which generate the two by two matrices with A and B. So a simple Grassmann algebra consisting of one nilpotent A. The second Grassmann algebra is consisting of one nilpotent B. They're compatible because the symmetric product AB plus BA is equal to 1. And then I generalize that to A1 up to AN for the Grassmann algebra generated by N vectors, A1 to AN, which are in the generated Grassmann algebra. And then I take the B's, B1 and Bn as the compatible Grassmann algebra. And all together, they form a basis of the Clifford algebra of CLN comma N.
Maybe if I can put one slide here after of this. Not here, but here. The idea of associated space. I don't know if this is related with the idea of using different Grassmann algebras for the representation of this. But here I am thinking about the associated space of one ideal in the space B. Then this associated space is built with here in like a vector form, but in the way that vector form is used to annihilate the multiform. Then I think the way that Professor Garrett is using splitting the algebra in terms of idempotents and annihilators maybe can be related with this. With idea.
Yeah, I think the difference is that I'm trying to define a new, so okay, take the vector space and the covector space, and I'm defining a new symmetric product between the two elements in a certain way. And I think that you can do that consistently because that's the way I get the structure of the Clifford algebra reflected by the coordinate matrices that represents that element. So, but that's a new product. Normally people don't define a product in that way between the algebra of covectors, the Clifford algebra or the Grassmann algebra of covectors and the Grassmann algebra of vectors. You can define a relationship by what I wrote down, saying they're compatible. Then you're just identifying, instead of writing A1 up to AN, the covectors are A1 star, B1, A2 star up to AN star. But think about those as just being nilpotence B, the B1 up to BN then. So I'm defining a new product between those elements then, the symmetric product. And I think you can do that. That's how I get to interpret a matrix as just the coordinates of a geometric algebra. Any matrix is represented as the coordinates of a geometric algebra using that. But the new idea then is to use a symmetric product of the covector space to be equivalent to this symmetric product on the vector space. You can, well, that's defining a inner product. You can define an inner product on the, well, that's the thing. Inner product is usually defined in terms of a vector times a covector is the inner product. But now we're defining an inner product on the covector space, which is analogous to the inner product on the vector space, which is symmetric.
Yes, because here we have a creation operator and an annihilation operator. And then we can define both in both space, in the space B and the dual space. We can define. And then I think that this can help to us to build one algebra that is going the same in the that runs in parallel in both space, in dual space and the space B. Then the connection between these two spaces are dimetric, are dimetric, and then the way that we can relate both are then the definition of metric in that space. I think that we can do that in this way.
Maybe you could define the matrix product in terms of the product between some product between a vector space, the Guzman algebra of the vector space and the Guzman algebra of the covector space. Define the matrix product for me in terms of those two algebras. That would be the same then.
Yes. That I remember that so one way of doing that are the dyadic product.
A dyadic,
Dyadic between.
I've seen that, that's right.
Then we can use the dyadic products in this way, and then one is the dual of the other. One matrix is the dual of the other in the dyadic.
Okay, I think that's it. I think that's probably the way to do it, was using the dyadic product to relate the two ideas together then.
Yes, yes. And okay, but
isn't this actually part of the tensor algebra, so that we would write like V tensor V star? And
yeah, I think that's true too. That's right. Yeah, what's the relationship between the tensor algebra and the dyadic algebra? Algebra dyadics. They're almost the same, aren't they?
Because dyadic product is like how would you say, if you have a tensor I, but when you how would you say this? when you because if we put these two indices equal, then we have here an scalar. Then we go from matrix to scalar here. And we need to introduce here one operation that is, what is the word?
You write here a superscript K and subscript K, is that?
Yes, yes. Here
So it's like a contraction?
Contraction. Then a contraction is the way of building the Adix product.
Yeah, that's the way of defining the tensor product too, by in terms of the vectors and the covectors. Symmetric.
Yes.
Yeah.
Mm-hmm. Mm-hmm. And then we can build in this way, and I think that what are because if we have this I d xj, then when we when I xj, when we contract these two elements, we get an scalar.
Yeah, that's what we identify the partial xi with the directional derivative, which is the gradient operator dotted with the vector, the directional derivative in the direction of a vector. So,
yes.
So EI dot the gradient gives you partial xi.
Okay. This in this slide, I introduced this because it is used the way that we can now using this idea to split the space. Because if the dimension of the space is n, then we can split the space with one part a vector and one part covector. And those are related through the associated space of one idea.
Yeah, that's right. So A plus B is a Euclidean vector, E1, and A minus B is F1. It has square minus 1 then. So that's how we're getting the Clifford algebra of the different signatures, 1, 1.
Okay.
So so take the sum of a vector with the covector A, and we're introducing a product on that, really. The geometric product is what on those two vectors then. That's just, it's just a slightly different way of looking at things. That's the whole confusing thing that has stopped it, I guess, from being recognized universally. It's too damn many identities in Clifford algebra. People don't want to master it. But it's the same as with matrix algebra. You can think about the Clifford product as being equivalent to the matrix product because it's isomorphic to a matrix algebra.
Okay.
But the matrix algebra doesn't have this notion of duality sort of inherent in.
Well, that's right. Matrix is considered to be, doesn't have a metric at all, but but it does have matrices which are anti-commutative and matrices which are commutative. So that's the more basic idea of a matrix algebra, is picking out those elements which are commutative or anti-commutative, which you don't have in just a pure Grassmann structure. But you do have when you take a Grassmann algebra and what I call compatible Grassmann algebra, then you have that structure then.
Okay. Okay, in these slides before I introduced the concepts of derivation, but at the end I want to speak about the observer in this way, like a way of splitting the space using an idempotent, and then if we split the space in this way, we can define with this an observer.
As an idempotent.
Idempotent, yes.
You see, that's what I did. I defined the idempotent AB, and that corresponds to the matrix with 1, and then everything else is 0, 1, 0, 0, column 0. Anyway, it's the same idea that we're talking about.
Yes, because here we have defined the observer plus the complementary part of this is equal to identity. That is the relation that you use, Professor Garrett, in the complementary numbers.
Yeah, yes, that's correct.
But then this endomorphism, is it composition of endomorphisms something like Clifford product?
That's right. It's equivalent to it. Well, there's many equivalents. There are many isomorphisms between matrix algebra, depending upon what, like, for example, quaternions. I think that's the big mistake of the last century or 2 centuries ago, that they did not identify matrices directly with Clifford algebra. That they should have done that, and then we wouldn't be having it. It would just be recognized today. It's still not. Instead, they divided it up into vectors and covectors and so on. That's the more accepted language today. Well, category theory is the other part of that, I guess. The complete generalization of it.
But here we construct this endomorphism from a vector space and its dual, right?
Yes.
And if we could extend these vector spaces and the dual vector space into Grassmann algebras, if we wished, right? So
that's
then,
exactly what I'm doing, actually.
so instead of, so if when we write, M tensor M star, we're thinking of the tensor product like as resulting in a tensor of type 1, 1, right?
Exactly.
Yeah.
But if these were Grassmann algebras, then we would have something like n, n.
Exactly. Yeah, and that's how we can identify with nilpotents. That's the thing with a matrix algebra. You don't think any metric is involved in the definition. Well, it isn't involved in the definition of a matrix algebra. But with Clifford algebra, you usually associate that with a metric. but it's not necessary. You can instead define Clifford algebra in terms of two compatible Grossman algebras. And that shows you the symmetric and anti-symmetric structure of a matrix that's built into the idea of a matrix, really. And that's, of course, symmetry and anti-symmetry are exactly what's most important in what fermions and bosons, you know. So that's why Clifford algebra, I think, is so successful using for physicists. Theoretical physics is built upon symmetry and anti-symmetry in quantum mechanics and so on.
But the ideas of Professor Osiewicz was to relate covectors with waves and particles with vectors.
What was that one more time?
Yes, here the idea is that a vector is related with particles, and a covector is related with waves. Then in this, if we presented the split of the space in this way, the idea of vector covector, the duality particle wave have not problems, because in the formulation is explicit this idea.
Okay.
Then okay, then those was the principal ideas. I only write again here in terms of the different notation, suggesting the concept of time and space. But it's the same that before.
Okay, well, yeah, 1-1 tensor. Well, I think that's the idea of how to put it together. You need to define, from my point of view, on the covector space, you need to define the structure of the symmetric of an inner product of covectors without going. That's what makes it difficult, really, because normally you don't think about covectors as having a symmetric part, or defining in terms of a symmetric and skew symmetric part as you do with vector. You can do that with a vector space, but it's conceptually not so clear with the covector. But they're both vector spaces, so you can introduce a new product, if you like, that's symmetric on the covector space as well. Why not? It's a vector space.
Okay, this was that I had prepared. Then
well, here this third point, you have tau t equals 1.
yes.
Now, is there any?
This is
okay. That's like compatibility. That's my compatibility condition.
Yes, is the same. That compatibility condition. Yes.
Yeah, the vector space has a. Okay, go ahead. Yeah.
So I think it's not the same as the compatibility condition where you wrote AB plus BA equals 1. Right?
Yeah, that's right. I would write tau t plus t tau is equal to 1. That's the way I would express it, the generalized product that I'm talking about. How do you put a symmetric product on the covectors? And I think that's the way you do it. Well, if you want to get a Clifford algebra out of that, which is exactly what I'm doing. That's the way I see it. So M is a Grossman algebra and M star is a Grossman algebra, but you relate those two Grossman algebra with element M times M's, with that relationship, tau T plus T tau is equal to 1. And that's it.
But what the connection I can see here is that this endomorphism kappa, the endomorphism kappa looks something like an element of a Clifford algebra. I mean, because we can take the composition of endomorphisms as being related to the Clifford product.
Well, that's right. The M is an endomorphism, and so is the M star. They're both endomorphisms. You can write them like I say. One is a
no, at least not my understanding is that the kappa, the product of tau, the tensor product of tau in T, is an endomorphism.
Well, that's an idempotent, the way I'm looking at it.
Well, we can.
An idempotent is an endomorphism, so there's no problem with that.
But we could write, for example, kappa squared, and we mean that kappa composed with kappa, right?
That's an idempotent, right? It's equal to itself. Kappa squared is equal to kappa.
Yeah, as an operator. So kappa squared is equal to kappa, yes.
Yeah. I don't see a problem with that.
But
in fact, it's a primitive idempotent if you think about it.
But it isn't clear to me that if we consider all the kappas, that they necessarily form the Clifford algebra.
Well, the simplest case is the 2x2 matrices, which are identified with the Clifford algebra generated by A and B. Okay, A squared is equal to 0, B squared is equal to 0, and AB is an idempotent, squared is equal to itself. Well, that table I always show. So that's the simplest example. That's the Clifford algebra G11. A plus B is like a Euclidean vector. Its square is equal to 1. A minus B is minus 1. So that's considered the simplest example of what Jesus has on his screen. Kappa is equal to tau. I guess the tensor product, if you like, capital T. But now tau capital T plus T capital tau, that's just equal to 1. The identity matrix, if you like, and think about it, 2x2 identity matrix then.
But this third item here is not the same as what you just said.
Well, that's right. I'm introducing a product between the vectors and the covectors.
Here the idea of the third row is that the space is described with the product of tau and T. And then the one of in the right are the identity.
Yeah, kappa is an idempotent.
Idempotent, yes.
Okay, you agree with that? Everybody agrees with that idea, right? Kappa is an idempotent. But that's also an endomorphism in an endomorphism algebra generated by, 2x2 matrices, if you like, on that respect, looking at it. So think about it in terms of matrices. That's all we're doing, really. You can interpret this, what you've written down in terms of matrix algebra, 2x2 matrix for the simplest case that you have there. Well, anyway, I think that's the whole problem, though, with people's conception of Clifford algebra. They don't recognize it or don't think about it as in terms of an algebra of endomorphisms. Well, matrix algebra is the coordinate matrices of Clifford numbers, geometric algebra.
Yeah.
Generated by an algebra of nilpotents. That's why I like the nilpotent idea, because you're getting away from the idea of an algebra of vectors. Well, you have an algebra of nilpotents. That's the basic idea. And then you identify from those, you generate an algebra taking a product between, to find a product of these nilpotents. And it ends up being isomorphic to the algebra of matrices. Anyway.
Okay. Okay, then that's all that I had prepared for today.
Now, Professor Bill might want to talk about more next time when we meet in, what, 2 weeks again?
Yeah, well, I can give it a try. I mean, I'd like to, maybe I could say something about this observer algebra, but the work that I did with Oshevich quite some time ago was focusing on the notion that this observer algebra was Frobenius. So the notion of Frobenius is more general than Clifford algebra, at least from the part that to the extent that I understand. It's like it's a bialgebra. That is, it has both products and coproducts.
Clifford algebra.
Well, Clifford algebra, the work of Abramovich, is that the right name?
Yeah, Abramovich
and
Abramovich
and Fauser. They explored in cooperation with Oshevich. They explored the idea of the bialgebra structure of Clifford algebras. And I'm not sure then necessarily that we would want to say that, well, I'm quite sure that we wouldn't want to say that all Frobenius algebras are necessarily Clifford algebras. That would not be likely, but if we admit this bialgebra structure of Clifford algebra, then we might say that a Clifford algebra together with its bialgebra form a Frobenius algebra.
Let me just say one thing here. I have just been studying or looking at the history of Frobenius, and I learned that Frobenius gave the first proof of the Cayley-Hamilton theorem. This surprised me because that was what the key idea of my thesis that set me off on developing the ideas of linear algebra in Clifford algebra was when I could formulate the proof of the Cayley-Hamilton theorem entirely in terms of Clifford algebra. And the most simplest case was the idea of a 2x2 matrix. But that's very interesting about Frobenius, what he did. And he lived at the same time as Clifford, Hamilton, and Cayley. And it's too bad those mathematicians didn't work closer together. We wouldn't be having this conversation today. It would be developed the ideas differently. That's the whole problem. Those guys didn't cooperate with each other. Well, Clifford did the awful thing of dying, but
yeah. Well, but okay. In 2 weeks' time, I can see what I can do to present some of the work that I did with Oshevich, which was defining was to make the assumption that the observer algebra was necessarily Frobenius, and therefore it has this bi-algebra structure, and you expect then to be able to define the unit in this algebra, or more generally to examine the center of the algebra. And one of the things that I showed was that the center has only one element, that it has.
That's
this,
an idempotent. That's idempotent.
well, it acts as the identity, right? So that this.
Yeah,
but,
AB plus BA is equal to 1.
But what is the one, right? That was the reason why I asked you when you presented that idea. Say, like, if you write one, is one the scalar one, or is one the?
Yeah, 1 is the
something
real
more
number
general?
1. But yeah, it's the real number 1. But we do that all the time.
Yes.
You know, you don't want to distinguish in Grossman algebra. You don't want to distinguish between a 0, 1 vector, 0, bivectors. It's just 0.
Well, I guess it's equivalent to saying that I didn't want to presume the algebra had necessarily had a unit, that it's not necessarily unital, but then to prove, in fact, that it does, that the only element of the center of the algebra is the unit, right?
That's an idempotent, right?
Well,
Okay,
and in fact, it's the only idempotent.
Yeah, I'd like to hear what you have to say more. I would be interested in, if you could.
I'll give it a try. I've tried to present this a couple of times. It involves some fairly interesting, maybe, applications of computer algebra. And the work I did at the time was using a computer algebra system called Axiom, which allowed, well, it has some tools that made these calculations fairly simple, at least conceptually simple. And one could do the same sort of calculations in Maple or in Mathematica, but to do them by hand, I think would be really close to impossible. And I guess that was the origin of the sort of work collaboration that I had with Oshevich.
Well, I'd like to hear more about this. You know, I had these conversations with Zbyszek 50 years ago in Poland. Well, as well as in Mexico too, when we were living at. So it would be very interesting to. You really continued on where I left off with Zbyszek, and of course Fesk as well. You know, I did then go to Universidad de las Americas in Puebla.
Mm-hmm. Yeah. Okay. Well, I'll see what I can do. So we'll meet again in 2 weeks. And I'll try to at least introduce the calculations that I did and why I think they are interesting. I can also sort of point out how Oshevich and I never came to a conclusion on this subject, right? Because he wanted to begin with a unital algebra and presumed that the algebra necessarily had an identity. And then when I showed him that the identity was something that you could calculate and that it wasn't something that you needed to assume from the beginning, it was a surprise, right? It was sort of like saying, why do we need this? Like, and it was arguments between us, something like saying, well, is the fact that should we say that the center of this algebra actually has two elements? One is the sort of trivial identity 1, and the other one is this non-trivial thing that also acts like an identity in some respects. And this was connected with some of the work that was done, that we were doing, like, or at least thinking about, in terms of the center of mass, because it wasn't, because when you deal with the Frobenius algebra, it would be nice to be able to, well, in fact, it is possible to define within this observer algebra the concept of center of mass, like as because each observer is like a massive body, and so within this Frobenius algebra, we can define another element of the algebra, which is like another maybe fictitious observer, which is equivalent to the center of mass.
Now, maybe you could start by defining a Frobenius algebra. That's not quite clear to me.
Yeah. But okay, yeah, okay. I'm just thinking aloud about what I should and should not say, right? Because it could be a long subject without much resolution. But
well, you know, there are many idempotents, but the most important idempotent is one in the real number system. Mm-hmm. And then if you generalize to have vectors which have square plus one, then you have many other idempotents. Well, you have primitive idempotents. That's an important idea as well. So A1 times B1 is an idempotent, A2 times B2 is an idempotent, and you put those together to generate the more general, well, you know, in matrix algebra, any number of ones down the diagonal is an idempotent. There are many different idempotents which you can associate with a matrix, of course. Mm-hmm. Anyway, I'd be very interested to see a definition of a Frobenius algebra to start with. I'm not quite clear on the concept.
Yeah, well, the way I would start with that would be using these graphical diagrams, the way Ushevich was fond of doing. But okay, I'll think about what we should talk about next week, but it'll be on that subject.
Okay, I'm looking forward to it.
Okay, well, we'll see you both next week.
I enjoyed it. Very good.
2 weeks. You say next week or 2 weeks?
No, I'm just saying in 2 weeks. 2 weeks time.
Okay.
Yes.
Okay.
Okay. So bye for now.
Bye. Thank you.